In this session, we consider the idea of total probability. And the idea is that we can, sometimes it might be difficult to evaluate the probability of an event directly. And we can do it by adding up the probabilities of some associated conditional probabilities. Okay. So, you know the definition of conditional probability, you know the multiplication rules. So we're going to use those to find probabilities of events. Okay, using the theorem of total probability. Okay. So first we need the idea of a partition. So let's say that I have my experiment is flipping a coin and recording the results. So the sample space S is equal to HT. Now I can break that S up into two mutually disjoint sets. The one containing only H, the one containing only T. So those two subsets, if I take their union, then I get S, and they're disjoint. Their intersection is empty. Okay, well, let's try another one. And now I'm rolling a die, and I record the results. 1, 2, 3, 4, 5, 6. Those are all the possible results. And that's my sample space. Now I'm going to break that sample space up as the union of three mutually disjoint sets. So let's say there's one event rolling a 1 or a 6, there's another event rolling a 2 or a 5, and there's another event rolling a 3 or a 4. And if I take the unions of these events, I would get S. And if I take the intersection of any of these events, I would get the null set or the empty set. Okay, so here S is the union of three mutually disjoint sets, and the sets are said to partition S. Okay, so definition of a partition. Supposing that you have sets subsets of S events, B1, B2, B3 up to Bk. We say that they partition the sample space S if their union gives you S, and if their intersection of different of these BIs, if BI intersection BJ, that's empty whenever I is not equal to J. Okay, and yeah, the sets should be non-empty themselves. Okay, so for two coin tosses, find two different partitions of S, right? So you've got HH, HT, TH, and TT. That's your sample space S. As an exercise, find two different partitions of this S. Okay. Now, supposing that B1 and B2 partition S, and there's some other event A. Now, if I take A intersection B1 and I take the union with A intersection B2, B1 and B2 are disjoint. So there's some elements of A are in B1, some elements of A are in B2. B1 and B2 are disjoint, and put together, B1 and B2 make up all of S. So A is equal to A intersection B1 union A intersection B2. So it might be that you're asked for the probability of A, but for some reason that's difficult, and it would be easier to find the probability of A intersection B1 and to find the probability of A intersection B2. So that's what the idea of total probability gives us. And if you use the distribution laws that we talked about before, you can prove this set identity. Now, Okay, so if you want the probability of A, then the probability of A would be the probability of A intersection B1 plus the probability of A intersection B2 minus the probability of the intersection of these two sets. But the intersection of these two sets is empty because every element in here is in B1, every element in here is in B2, and B1 and B2 don't overlap. So the probability of the intersection of these two sets, A intersection B1 and A intersection B2, that's empty. So the probability of that intersection would be 0. So then we just have that the probability of A is the probability of A intersection B1 plus the probability of A intersection B2. Remember that we are using the fact that B1 and B2 partition S. Right? You can't just take any B1 and B2 and expect this to work. Okay. Now, what's probability of A intersection B1 in terms of conditional probabilities? Remember, we had the multiplication rule. So the probability of A intersection B1 is the probability of B1 times the probability of A given B1. And similarly, by the multiplication rule, the probability of A intersection B2 is the same as the probability of B2 times the probability of A given B2. All right, so let's do an example using these ideas. Okay, if I draw 2 cards from the top of a well-shuffled deck, what's the probability that the second card drawn is the Queen of Spades? Okay, so before we use this new idea, think in terms of old ideas. What should it be? Well, if I lay out upside down, I lay out all 52 cards. And I pick one. Happens to be the second one. What's the probability that that would be the Queen of Spades? 1 out of 52. Okay, so that's my guess that the answer should be 1 out of 52. Okay. Now, how would you do this problem using this this idea here, this formula here? Well, let's say in order for the second card to be the Queen of Spades, you know, if the first card is the Queen of Spades, then the second card won't be the Queen of Spades, right? And so we can partition the sample space for this by saying F is the event that the first card drawn is the Queen of Spades. Then the complement of F is the event that the first card drawn is not the Queen of Spades. And the sample space, well, it's either the Queen of Spades or it's not the Queen of Spades, right? All events will have either this criteria or the other criteria, but they will all fall into it. The element of any other event falls into F, or it falls into F complement. Okay, so these two events partition the sample space. Now, let's say that you're going to, A is the event of the second card being the Queen of Spades. Then the theorem of total probability, that's this theorem over here. It says that the probability of A is the probability of F times the conditional probability A given F plus the probability of F prime times the probability of A given F prime. Now let's think about these. Probability of F. What's the probability that the first card is the Queen of Spades? That's 1 out of 52. The first card could be any one. If it's properly shuffled, there's no cheating going on. While the first card could be one of any of the 52 cards equally likely. So 1 out of 52. Okay, what's the probability of A given F? What's the probability that the second card is the Queen of Spades, given that the first card was the Queen of Spades? Or if the first card was the Queen of Spades, there's no way that the second card can be the Queen of Spades. So this probability is 0. Okay. Probability of F prime, the probability that the second card, so the probability that the first card is not the Queen of Spades. Well, that can happen for any one of 51 cards out of 52 that could be equally likely to be the first card. Okay, so that's 51 out of 52. Probability of F complement is 51 out of 52. Now, what's the probability that the second card is the Queen of Spades, given that the first card was not the Queen of Spades? So you picked up one card, and it was not the Queen of Spades. Now there remain 51 cards, and it's a fair deck, so any one of those 51 cards could be the Queen of Spades. So the probability that the second card is the Queen of Spades, given that the first card was not the Queen of Spades, that's 1 out of 51. Okay, so if we add all that up, that's 1 out of 52. That's kind of what we expected, right? Now we can generalize this. In the previous example, we were talking about partitioning into two sets, right? So the sample space into two sets. There's F and F prime. The union is S, and they don't overlap. They're disjoint. But in principle, you could do it in different ways. Okay, so let's say that there are K non-empty sets, B1, B2 up to BK. The probability of any of those events occurring, the BIs is not equal to 0. And the intersections are empty. So these the union of the BIs is S. The intersection of BI intersection BJ, that's equal to the null set unless I equals J. And the probability of any given BI is not equal to 0. So the BI partition S. And then the probability of A is equal to, if you sum the probability of BI intersection A. And then if you apply the multiplication rule to this probability, that's the probability of BI times the probability of A given BI. And then you sum that from I equals 1 to K. All right. Okay. So let's try another example. You're going to draw 2 cards from the top of a well-shuffled deck. What's the probability that the second card drawn is a queen? Well, let's set up our partition. Let F be an event that the first card is a queen. Let F complement be the event that the first card is not a queen. Then F and F prime partition the sample space. Okay. Let A be the event that the second card is a queen. We want to find the probability of A. Then by our total probability idea, the probability of A is the probability of F times the probability of A given F, plus the probability of F complement times the probability of A given F complement. Okay, so what's the probability of F? F is the event that the first card is a queen. Well, that's 1 out of 52, right? Sorry, 4 out of 52. There are 4 queens out of 52 cards. Right? And all the cards are equally likely to come up. What's the problem? Okay, so that's the probability of F is 4 out of 52. What's the probability of F complement? What's the probability that it's not a queen? Well, there are 48 cards, which are not queens, and there are 52 cards in total, and they're all equally likely to come up. So that's 48 out of 52. Okay, what can we figure out here? Probability of A given F. Let's suppose A again. A is the event that the second card is a queen. What's the probability that the second card is a queen given that the first card was a queen? So if the first card was a queen, then there are 51 cards left over, and one of the queens is gone. So there are 3 out of 51 cards that are queens, and any card is equally likely to come up. So probability of A given F prime is 3 out of 51. Okay. What's the probability of A given F complement? What's the probability that the second card was a queen, given that the first card was not a queen? Okay, so you took away 1 card. There are 51 cards left. And there are still 4 queens, right? The first card was not a queen. So there are 4 queens out of 51 cards. Each card is equally likely to come up when we draw it. So probability of A given F complement is 4 out of 51. So now we figured out all these probabilities. Multiply and add, we get 4 out of 52. Okay. Once again, if you think about it, I lay out all the cards upside down. They're well shuffled, fair, no cheating. I pick the second card and I turn it over. What's the chance that it'll be the queen? Well, that could have been any card out of the 52, and there are 4 queens, so 4 out of 52. Okay. Now, one place where this total probability idea gets used is in the simple analysis of survey results. So let's say that 60% of adults support the QQQ party, 30% support the RRR party, and 10% support some other party, whatever. Might be multiple parties, but that 10% support is divided. Okay. Now, the survey also says that 40% of the QQQ supporters dislike the new Superman movie. 65% of the RRR supporters, they dislike the new Superman movie. And 50% of third-party supporters, sorry, 55% of third-party supporters dislike the new Superman movie. Okay. What is the probability that any randomly selected adult dislikes the new Superman movie? Okay. Okay, so let me try partitioning it this way. I can partition all of these adults into those that like the QQQ party, those that like the RR party, and those that like some third party. So let Q be the event that an adult is a triple Q supporter, and let R be the event that an adult is a triple R supporter, and let T be the event that the adult supports some other party. Okay. Now these partition that set of adults, right? Because there's no overlap. you made a definite commitment to one party or the other when you answered the survey. Okay, let A be the event that an adult dislikes the Superman movie. So we want to find the probability of A. So that's the probability of A and Q, A intersection Q, plus the probability of A intersection R, plus the probability of A intersection T, or using the multiplication rule, right? That's the probability of Q times the probability of A given Q, plus the probability of R times the probability of A given R, plus the probability of T times the probability of A given T. Okay, so the probability of Q we were given is 60% support triple Q. Probability of R, we were given that 30% support triple R. And the probability of T, we were given that 10% support third parties. What else were we given? We were given that 40% of the QQQ people dislike the new Superman movie. So the probability of A that an adult dislikes the Superman movie, given that the adult is a QQQ supporter, so probability of A given Q is 40%. This is the probability of A given R is 65%. And the probability of A given T is 55%. So we have these numbers, 0.4, 0.65, and 0.55. We add them all up, we get 0.49. So the probability that any given adult in our survey disliked the new Superman movie is 49%. Okay. Here's ideas that are used in sampling. So let's say a factory makes widgets, and there are two factories. There are two machines in the widget factory. So machine 1 makes 60% of the widgets. Machine 2 makes 40% of the widgets. 4% of the widgets made by machine 1 are defective. 1% of the widgets made by machine 2 are defective. I want to know what is the probability that a widget was made by machine 2 given that it was defective. Okay, so here are some events that we can think about. M1 is that the widget is made by machine 1. M2 is the event that the widget is made by machine 2. D is the event that the widget is defective. And D complement is that the widget is not defective. What are we looking for? We are looking for the probability of M2 given D. Okay. So what have we been given? The probability that, all right, machine 1 produced 60% of the widgets. So the probability of M1 is 0.68. Machine 2 produced 40% of the widgets. So if all of the widgets were coming into the file and we picked up one of them at random, there's a 0.6 probability that was made by machine 1 and a 0.4 probability that was made by machine 2. Okay, now 4% of the widgets made by machine 1 are going to be defective. Okay, so what we're saying is that the probability that a widget is defective, given that it came from machine 1, is 0.04. And similarly, the 1% of the widgets produced by machine 2 were defective. So the probability that uh, that a widget is defective, if you know that it came from machine 2, then there's a 1% probability that the widget is defective. Okay, what do we want? We want the probability of M2 given D. Okay, so we have D given M2, but we don't have M2 given D. Okay, all right. So we want the probability of M2 given D. All right, so definition of conditional probability. That's the probability of M2 given D divided by the probability of D. Okay. Now the probability of D is not given, but okay, we can say this. We have a partition. We can have M1 and M2 partition. The widget is either made by machine 1 or machine 2. So the probability that it's defective is the probability that it was made by M1 times the probability that it's defective given that it was made by M1, plus the probability that it was made by M2 times the probability of D given M2. Okay, so that's just total probability, with the partition being the two sets, the two sets M1, M2 partition the sample space. Okay, so then the desired probability is the probability of M2 given D is the probability of M2 intersection D divided by the probability of D. And now the probability of D was this by total probability. And so we replace probability of D by this formula that comes from total probability. So the probability that it was made by machine 2, given that it's defective, is the probability of M2 intersection D divided by probability of M1 times the probability of D given M1 plus probability of M2 times the probability of D given M2. Okay. Now, what do we know? We know probability of M1, we know probability of M2, we know probability of D given M1, and we know probability of D given M2. Okay, so we know all the probabilities in this denominator here, all of them we know. We don't know probability of M2 intersection D. Okay. Oh, well, let's use the multiplicative rule again. Right? The probability of M2 intersection D is the probability of M2 times the probability of D given M2. Do we know probability of M2? Yes. Do we know probability of D given M2? Yes. Okay, so we replace probability of M2 intersection D by this, which comes from the multiplication rule. Now we have all the numbers that go into this, and we put all of those in. We get 0.1429. Okay. Another example. Okay. So we have the Acme atomic power plant. If something is wrong, then the alarm will go off 99% of the time when something is wrong. So the probability that the alarm goes off, given that something is wrong, is 99%. Okay, when everything is fine, even when everything is fine, the alarm goes off 1% of the time. So the probability that the alarm goes off given that everything is fine, is 1%. Okay? The probability that something is wrong at any given time is 1%. Okay? Maybe this is reminding you a little bit of the medical test example. Okay, so if something is wrong with the plant 1%, something is wrong with the plant 1% of the time. Now, if the alarm goes off, what is the probability that something is wrong? Okay, so the alarm goes off, should I be running for my life or not? Okay, okay, so let's think of it this way. 1% of the time, let's think in terms of 10,000 days, okay? So the plant has a problem 1% of the time, so that would be 100 days. So out of 10,000 days, there are 9,900 days with no problem. And there are 100 days with a problem. Okay. And so the information we're given is that of the 100 days when there is a problem, 99% of that is 99. 99 days the alarm will go off, and 1 day out of the 100 when there is a problem, the alarm will not go off. Okay. When there's no problem, that's 9,900 days. 1% of the time, that is 99 days, the alarm will go off. So out of 10,000 days, there are 99 days when the alarm is going off for no reason. So the alarm is ringing 99 days when there, and on those days there is a problem. And it's ringing. And it's ringing 99 days when there is no problem. So the number of days of the alarm is ringing are equal. So there's a 0.5 probability that there is a problem when the alarm goes off. And since it's an atomic power plant and there's a 50% chance that something is wrong, probably should take some precaution. Okay, so that was one way of doing it. Sometimes there's more than one way of looking at a problem. Let's look at it again using conditional probability multiplicative proofs, not the total probability. So let A be the event that something is wrong. B is that the alarm goes off. What are we given? We're given that the probability that the alarm goes off when something is wrong is 99%. The probability that the alarm goes off when nothing is wrong, A complement, is 1%. And we're given that 1% of the time something is in fact actually wrong. So that's 0. That's also 0.0. What do we want? We want to find the probability that something is wrong given that the alarm has gone off. That by definition is the probability of A intersection B. Okay. Well, what's the probability of B? What was B again? A is that something is wrong and B is that the alarm goes off. So what's the probability that the alarm goes off? Well, the probability that the alarm goes off is now A and A complement, they partition S, right? As any set and its complement will partition the sample space. Any non-empty set and its complement partition the sample space. So the probability of B is equal to the probability of B get B intersection A plus probability of B intersection A complement. And we can rewrite A intersection B, probability of A intersection B as probability of A times the probability of B given A. And we can rewrite the probability of A intersection, sorry, of A complement intersection B as the probability of A complement times probability of B given A complement. Okay. So now we can replace this probability of B in our definition of the conditional probability. We can replace it by this line here, which is total probability. So the probability of A given B is equal to the probability of A intersection B divided by the probability of A times the probability of B given A, plus the probability of A complement times the probability of B given A complement. Okay. Do we have the probability of A intersection B? All right, I think we have all the others, but we don't have the probability of A intersection B. But again, the multiplication rule says that you can rewrite this probability of A intersection B as the probability of A times the probability of B given A. So we replace probability of A intersection B in the numerator with probability of A times the probability of B given A. And you put that in the numerator. And right, we leave the denominator as before. Now we had these probability something's wrong is 1%. The probability that the alarm is ringing, given that something is wrong, is 99%. Something wrong is 1%. Of these, right? So these numbers are the same as those numbers. And the probability of A prime, A complement is, right, something is wrong 1% of the time, something is not wrong 99% of the time. And the probability that the alarm is ringing even though nothing is wrong is 1%. So we put all those numbers in and we get half, as we suspected from before. Okay, so those are some examples using total probability, and they this builds up to the notion of a very important law, big law. Okay, so I'll see you next time.